The Karl Terzaghi Lecture was established by the Soil Mechanics and Foundation Division of IFCEE in 1960 to honor Karl Terzaghi, the father of soil mechanics. Each year, the Board of Governors selects a distinguished engineer to deliver their Terzaghi Lecture at our annual conference. Next slide. There have been 53 recipients of this award beginning with Ralph Peck in 1963. And I must say that this list of award recipients is very impressive. And we actually have several of our lecturers with us today. So it gives me great pleasure to introduce Dr. Bonaparte, Dr. Rudy Bonaparte, professional engineer, diplomate in geotechnical and engineering, member of the National Academy of Engineers, as well as fellow in IFCEE as the 54th Terzaghi Lecturer. Dr. Bonaparte has more than 35 years of geotechnical and geoenvironmental engineering experience. He received an undergraduate degree in civil engineering from UT Austin, where he was the outstanding undergraduate, and then a master's and PhD from University of California at Berkeley. He started his career at Woodward Clyde Consultants in San Francisco, and then moved to Atlanta and joined the Tensar Corporation. So I'm just going to show, and I think this is relevant to students. Rudy started off as a student like you, and the two slides on the left, he was a student at Berkeley. There he is in the soils lab with his other constituents. You can see, maybe like you, your first job may not have been what you thought it would be. And that is the picture in the upper right. So as his career progressed, he learned that he couldn't do it all on his own, and he relied on other experts, friends he may have made in college. So you students, this is a chance for you to get to know everybody because you're going to be working with your geotechnical family for the rest of your lives. The bottom picture is that's with Rudy Bonaparte, along with Bob Backus. Many of you know Bob Backus, as well as Ken Stokey. So Ken Stokey has some specialized capabilities, and he was brought in to help us with a project. And Rudy, in his practice, has done that quite a bit. So after Woodward Clyde Consultants, he moved to Atlanta, joined the Tensar Corporation. You can turn it to the next one. And became application technology manager. From there, he moved to Geosyntec Consultants when we were only a 10-person firm, and that is where he stayed until today. He served as president and CEO for more than 2 decades and is currently the firm's chairman. For many years, Dr. Bonaparte worked under contract to the U.S. Environmental Protection Agency to conduct research into the design and evaluation of waste containment systems. Through this work, he's widely regarded as a national leader on the topic. Then he took these findings of this research into his practice. In 2016, he was awarded the IFCEE Opal Lifetime Achievement for his innovative approach in landfill and liquid impoundment design. He was elected to National Academy of Engineers in 2007. He's a recipient of the Crows Award in 2000, and he's the author of more than 50 peer-reviewed papers, as well as book chapters and other major reports. I mean, in addition to this, Rudy has been a mentor to me, so I've worked with Rudy now for over 30 years at Geosyntec Consultants. So the GI has selected Dr. Bonaparte to present the Terzaghi Lecture in recognition of his more than 30 years of efforts to advance the state of practice in the design and evaluation of waste containment systems. And I'm very pleased to introduce Rudy as our next Terzaghi Lecturer.
Well, Beth, thank you for that kind introduction. And Yusef and the Geo-Institute, thank you very much for this honor. I am really, truly honored to be here today. And it's extra special to be here, seeing so many longtime friends and colleagues in the audience. So thank you for showing up. I think every Terzaghi lecture needs to show some sort of lineage back to Professor Terzaghi. And my lineage is here. And it's through my academic mentors, Roy Olson at the University of Texas and Jim Mitchell and Mike Duncan at the time at UC Berkeley, all of them former Terzaghi lecturers. I'd also like to acknowledge Jean-Pierre Giroux, another former Terzaghi lecturer who was my longtime colleague, mentor, and friend at Geosyntec Consultants. And lastly, Dave Daniel and Bob Kerner, who I had the good fortune to work with over many years on some of this EPA research that Beth described a moment ago. And so I've been fortunate in that regard. I want to continue with the thank yous for just one more moment. Throughout my career, I've had the good fortune to work with many academicians in the area of waste fills. And some of them are shown here, and I'd like to acknowledge them and say thank you for how much you've enriched my career. I'd also like to thank my colleagues at Geosyntec, where I've worked for the last 32 years. We have a great group of people. I'll be talking about 6 case studies today, and those case studies are all projects where we performed forensic investigations of failure. And the people on this slide, some of the people on this slide, were the ones that conducted much of the work, so thank you. My lecture outline is shown here. It's pretty straightforward. I have a few introductory slides. Then I'm going to roll back the clock to the early to mid-1980s when U.S. Environmental Agency regulations were first being promulgated, and the age of modern waste fills, modern landfill facilities was just coming into its own. And during that period, there were a number of notable waste fill failures from which we learned a lot. And what we'll do is take a quick look at those failures and see what we learned. And we'll see by the mid-1990s, we had learned a lot. In fact, I think many of us had a lot of confidence that we had the problem solved. We knew how to design these facilities to be safe and not undergo slope stability failures. We're then going to fast forward to the current decade from 2010 to now, and we'll see that failures are continuing to occur. So we'll look at a few of those. We'll ask ourselves the question why. We'll see what lessons we can learn, and we'll wrap up this lecture with some observations and recommendations in light of the continuing challenges. So just a few points of background. When we talk about waste fills, we're talking about a large population of structures. There are about 2,000 active municipal solid waste landfills in the United States. There's about 10,000 closed municipal waste landfills. There's thousands of different types of industrial facilities, coal combustion residual impoundments, mine tailing piles, hazardous waste landfills, low-level radioactive waste disposal facilities. There's lots of structures. In addition, if we think about internationally, there's many times that many structures. And some of these are well engineered and some of these are not so well engineered. And in fact, there have been some truly catastrophic failures on the international stage in the last several years. I'm not going to be talking about the international projects today. I'm going to focus on U.S. facilities and U.S. standards of practice. When we think about stability at a landfill or any other type of waste fill, there are a number of different failure modes that we need to consider. For example, sliding or failure through the waste mass itself, failure through the waste mass and then along interfaces of the liner system, foundation failures, stability issues with perimeter berms or stability berms. I've been involved in projects sited in canyons where the stability berm itself is over 200 feet high, so these can be large structures. And of course, liner system veneer stability and cover system veneer stability. I'm not going to talk about veneer stability issues. That could be a lecture onto itself. We've seen problems in the past. We continue to see issues and problems today, but I'm not going to be talking about that. So geotechnical design engineers must be cognizant of multiple static and seismic failure modes, and they must look at these things for a facility at every stage of the facility life. Many of these structures have operating lives that are measured in terms of decades, and they may have a dozen or more different interim configurations. So there are many different potential failure modes. There are a number of different configurations during the operating life, and all of this needs to be considered in seismic zones, both from a static perspective and a seismic perspective. So you can get a sense of some of the challenges that are associated with evaluating the stability of these kinds of structures. Well, why is it important? Well, it's important because unstable waste fills pose risks to lives, property, and the environment, plus economic loss for the owner-operator. And I'll illustrate that with just this one slide. This is the Operating Industries, Inc. Superfund site in Southern California. This was described in Professor Ed Kavazanjian's 11th Peck lecture. And you can see this is a large facility. It rises over 200 feet at a very steep angle adjacent to a major freeway, the Pomona Freeway. There are 2,100 people that live within 1,000 feet of this facility. So just imagine, and I should say it's full of both solid waste and liquid hazardous waste. So just imagine if during a major earthquake, this structure were to fail and slide into the Pomona Freeway or into a surrounding neighborhood. It would be catastrophic. This illustrates very simply the importance for geotechnical engineers of correctly evaluating the stability of these structures. So where did we start? Let's go back to the early days of U.S. Environmental Protection Agency regulations, and that would be from the early mid-1980s to the early 1990s. And what we see is that there were a number of waste fill failures that occurred that drew the attention of regulators, owner-operators, and geotechnical engineers. Some of those failures are shown here. I'd like to, just in the next few minutes, talk about three of them: Kettleman Hills, Crossroads, and the Rumpke landfill failure. Many of you know about Kettleman Hills. This was a hazardous waste landfill, and we see in the photograph on the left-hand side of the slide where a mass of about 600,000 cubic yards of hazardous waste slid on top of a liner system approximately 35 feet over the time period of several hours. We see the direction of movement in the slide. Basically, this was one of the first double composite lined landfills in the United States, one of the first landfills with a truly modern liner system designed to high standards with an understanding of the issues related to the stability of the liner system and the interfaces in it. If we look at the right-hand side of the slide, we see the double liner system that underlies the base of the landfill. And you can see that it has a lot of components to it. The brown layers are compacted clay liners. The black thin layers are geomembranes. The tan layers are drainage layers, and the white layers are geotextiles. So you can imagine that there are a lot of interfaces, a lot of planes within the sliding liner system upon which sliding could occur. And the designers were cognizant of this, and they evaluated it. But they just didn't know enough at the time to understand all the things that needed to be evaluated to get it just right. Forensic investigation that was conducted after the failure revealed a translational sliding mechanism along liner system interfaces. In fact, the sliding mechanism was determined through the forensic investigation, which I should mention was conducted by Geosyntec, but much of the testing that was done afterwards was done at UC Berkeley by Ray Seed, Harry Seed, and Jim Mitchell, showed that the critical slip surface was between the smooth secondary HDPE geomembrane and the compacted clay liner. The clay liner at this site was compacted wet of optimum. It had between 2 and 5% bentonite mixed into it, and it was consolidated without any drainage boundary because of the presence of the geomembrane under the weight of the fill. This created an undrained condition at the interface that was weak and led to failure. In fact, the testing that was conducted showed that the residual interface strength of the geomembrane to compacted clay was only on the order of 500 PSF, equivalent to a soft clay. The testing also showed that although they wasn't responsible for the failure, that the geosynthetic interfaces were very weak as well. While testing had been done in previous years on these interfaces, the strengths that had been obtained were not as low as had as were obtained here at Kettleman Hills, and in fact, interface strengths of less than 10 degrees were determined. Residual interface strengths were found for a number of different interface conditions. So what can we learn from Kettleman Hills? Well, just a few things. There were many lessons, but just a few. Many liner system interfaces are weak and exhibit pronounced shear softening with residual strengths much lower than peak strengths. Liner system construction and waste placement operations can induce movements to mobilize post-peak interface conditions within the liner system. So it's not enough to just evaluate the performance of the liner system based on peak strengths, but one also needs to look at residual interface strengths. We also learned that waste mass stability evaluations need to address all interim waste filling conditions at the time of failure. This was, the landfill was in an interim configuration, and that was not considered in the design analyses that had been conducted. And then importantly, geomembrane CCL interface strengths are sensitive to their compaction, moisture, and shearing conditions. And this led to a finding that really resulted in a conundrum, and that is that compaction conditions for a clay liner that favor low permeability for the geomembrane and intimate contact between, low permeability for the compacted clay liner and intimate contact between the geomembrane and the compacted clay liner to create the composite liner condition are also conditions that create low interface strengths. So the conditions for environmental protection work counter to the conditions for interface stability. And we know today we need to account for that in design. The second case study is one in Maine in 1989 called Crossroads Landfill. And you see the landfill cell that failed in the photograph. It's an 8-acre cell that failed retrogressively and rather quickly due to foundation conditions beneath the structure. So at this site, the Landfill Foundation consists of a very sensitive glacial marine clay silt layer with a highly overconsolidated crust that transitions down to normal consolidation at a depth of about 20 feet. The clay silt layer served as a liner beneath the material. There was no constructed liner, and there was also no leachate collection and removal system, so there was no way to get leachate out of this landfill once water infiltrated into it. And we'll see that that was part of the problem here. With the waste height at about 60 feet, and after a period of heavy rain, a rapid, roughly 1 minute, failure occurred, retrogressing across the site from the east side, which is the right side of the photograph, to the west side. And you can see that the failure morphology is represented by a series of 6 large waste blocks that essentially floated on the foundation soil as it failed from the toe of the east side of the landfill back across to the west side. So at a height of 60 feet, the design engineers believed the factor of safety of this fill was greater than 1.2. Why did it fail? Well, there are a number of reasons. First, the original design was based on laboratory testing of shear strength. So the shear strength was understood from a laboratory testing program. However, the designers assumed a unit weight for the fill, for the waste itself. And after the failure, they went out, the representatives for the owner went out and did field testing, large-scale testing to determine the actual unit weight of the material. And what they found is that the unit weight of the material, due to a high soil content and high moisture content, was more than 30% heavier than had been assumed in the design. So this creates a loading roughly 30% on the foundation, roughly 30% higher than had been considered in the design. Then also the effects of leachate within the landfill and the creation of pore pressures, both in the fill and seepage into the foundation, was not fully considered in the design. In fact, I'm not sure it was considered at all. And so post-failure testing showed that there were high liquid levels within the fill, and this was not fully considered. So the failure itself, as I said, began at the eastern toe of the landfill and retrogressed over the course of a minute across this entire 8-acre area. And what the trigger was determined to be was an excavation about 8 feet deep at the eastern toe for purposes of constructing a new landfill cell that was going to be lined up to modern standards. So this excavation was made, the strong crust was removed, the sensitive soil was exposed to a vertical face, a local failure occurred, and then it retrogressed back. And we see that illustrated in this drawing here on the slide. You can see the excavation at the eastern toe of the landfill and the retrogressive nature of the slide. So what did we learn from Crossroads back in 1989, nearly 30 years ago? Well, first, that waste unit weight is a critical design parameter, as it's the primary source of gravity loading in waste-fill structures. Secondly, a clear understanding of liquid levels and pore pressure conditions, both in the waste and in the foundation, is critical. Thirdly, each significant construction or operational change in the field needs to be evaluated by the design engineer before the change is implemented. In this case, the excavation at the toe was not evaluated by the design engineers, and the work was done, the construction was done in the field, and the failure ensued. And then finally, while I didn't talk about this, for soft soil sites such as this one, the waste filling schedule must account for the rates of consolidation and the rate of strength gain in the foundation. So this is a classical stage construction kind of problem. The third and last historical case study we'll look at is the Rumpke landfill failure in 1996 near Cincinnati, Ohio. And if you look at the photograph, you see a yellow line cutting through the disturbed waste area. That yellow line is the original toe of slope for the landfill. And it's the area to the south of that line, i.e. to the upper part of the photograph, that failed. And as the landfill failed, the material flowed a large distance beyond the original toe. And part of the reason it flowed so far is that that area to the north of the toe, to the lower part of the slide, was a deep excavation for a new landfill expansion. And so as the waste mass failed, it entered into the excavation and converted all that potential energy into kinetic energy and flowed a long distance. I should mention that Geosyntec performed the initial forensic investigation of this failure, but then others have studied it carefully as well, including Professor Stark, who evaluated it in a number of papers over several years, and I want to recognize that. So the story of Rumpke is interesting. Starting in the 1940s, waste was placed in ravines on the Rumpke property directly onto native clayey colluvial soils. Landfilling continued over the decades until 1996 when the failure occurred. Importantly, when the failure occurred, the landfill had been overfilled. In other words, waste had been placed to a substantial height above the permitted acceptable top elevation of the landfill, and that'll be important in understanding the root cause of this failure. A week prior to failure, tension cracks were observed at the top of the landfill in the location of the eventual headscarp. The morning of the slide, the toe of the landfill began to move, and increasing leachate seepage was observed at that location. At the same time, the cracking at the crest was accelerating, so clearly conditions were deteriorating. After several hours of gradually increasing creep rates, the slope failed retrogressively, starting at the toe and working very quickly up through the waste mass over a time frame of only a few minutes. So this was another very rapid failure. In that short time frame, 1.5 million cubic yards of material moved hundreds of feet into the excavation. This is a cross-section of the slide. Tim, I hope you don't mind. I borrowed this from one of your papers. I put a little color to it, but it shows nicely the conditions at Rumpke. And first, a forensic investigation showed that the slip surface extended at a near vertical angle from the landfill crest down to the, through the waste to the colluvial soil, and you can see the dashed red line there. And then along the interface, or actually in the colluvial soil, exiting at the toe of the slide. So a translational type mechanism was sliding on the colluvial soil layer. Post-failure testing of the colluvial soil conducted by Geosyntec and also conducted by Professor Stark resulted in fully softened and residual friction angles in the range of 20 degrees and 8 degrees, respectively. Leachate levels in the waste mass prior to failure were later estimated after the failure to be substantial, on the order of 20 to 30 degrees. This was a facility that didn't have a leachate collection and removal system. So once liquids got into the waste mass, there was no way to get them out other than infiltration into the ground or slow seepage out of the face of the landfill. Due to delays in opening the lateral expansion, the landfill top deck had been overfilled by 30 to 40 feet in the 18 months prior to the failure. And you can see that the dark brown waste material in this cross-section is the overfilled material. And you can see in how the 18 months leading up to the failure, waste well beyond the permitted limit was placed. And as a result of that, the face, the front slope of the landfill was also steepened. The reason for this was it was taking a lot of time to permit the new expansion for the facility seen on the right-hand side of the photograph. So delays in permitting led to the need to find a place to dispose of all of this waste, and the owner-operator decided to put it up on top of the existing landfill. So the main causes of this failure were the strain softening nature and low post-peak shear strength of the colluvial soil, coupled with the high liquid pressures, coupled with the overfilling of the landfill mass. In addition, there may have been things that contributed to the trigger that took this marginally stable landfill and said, this is the day that you're going to fail. There was an excavation at the toe of the landfill to cut new access around the expansion area that would have locally destabilized that area. At the same time, this had been a cold period in this part of Ohio, and it was known that there was freezing of leachate within the waste mass at the toe. In addition, there had been nearby blasting recently to remove rock for the excavation. So any of these things could have created forces that triggered the slide or contributed to the trigger, but none of them were in of themselves were the root causes. So what can we learn from Rumpke? First, that foundation conditions for old unlined waste fills must be thoroughly understood if additional filling, excavation, or expansion of the fill is planned. In this case, the overfilling of the landfill was not considered thoroughly through the design process prior to that filling. Secondly, strain incompatibility between the MSW, which is a relatively ductile material, and colluvial soil, which is brittle, can lead to uneven development of shear resistance and subsequent strain softening of the material, creating post-peak shear strength conditions along the sliding surface. Third, leachate buildup in old unlined waste fills can reduce slope stability over time and take an otherwise stable waste fill and through the buildup of leachate pressures within the facility ultimately lead to its failure. And then, as I mentioned a moment ago, there can be specific events that help to trigger a slide, such as an excavation at the toe, blasting, or freezing conditions. So, by the mid-1990s, through these failures and others, we had learned a lot, and we thought we knew what we were doing. And in fact, if we just take a moment and think of some of the high-level lessons learned, and there were many, here are just a few. First, and most fundamentally, that geotechnical site investigations are as important to the design of waste fills as they are to any other type of critical geotechnical infrastructure. Waste materials have geotechnical properties, strength, compressibility, unit weight, etc. And these must be reliably and evaluated, or if they can't be evaluated, conservatively estimated for design. And the same thing with liquid and gas pressures. We need to understand what they are or make conservative estimates of what they could be if we can't measure them for one reason or another, and to use as a basis for design. We learned that interfaces are important, and they can be weak, very sensitive to moisture conditions, and exhibit shear softening. And the standard of practice evolved such that interface testing was being conducted and should be conducted if there is any doubt about the adequacy of available databases to represent the project-specific conditions. We also learned that mobilized strength compatibility in this particular area of practice is very important and needs to be carefully considered with respect to waste, which is often ductile, geosynthetic interfaces, which are often brittle and strain softening, and foundations, which can be anything. They can be sensitive, brittle, silicon-sided, strain softening, undrained, and/or liquefiable. And then lastly, with respect to two operating points. First, as I mentioned earlier, waste fills can undergo multiple configurations, and those need to be understood by the design engineer and accounted for in the design. This requires close communication between the owner-operator and the design engineer. That communication wasn't always happening, and we see it's still not always happening today. And then finally, decisions are made to change things in the field. You have a design and the contractor or the operator wants to change things around. That needs to be communicated back to the design engineer before that change is made, and that's not always done. So this is critical that owner-operators, contractors, everyone be cognizant of this fact. If you're going to change things from the design assumptions, it should be communicated to the designer. Oftentimes, the design engineer goes away when the design is done. The facility's operated for 10 years, things change, and no one comes back and checks on it. And moreover, with facilities with this long of a design life, oftentimes people change. Someone retires, the original design engineer isn't around anymore, the facility's been sold 3 times to new owner-operators and the records are lost. So this is a significant challenge. But we felt good in the mid-1990s. We thought we knew what we were doing. We could design anything, no matter how tall, how big, how ambitious. And so let's fast forward to this decade. And I've titled this section of the talk, Continuing Challenges, which would make you think that everything isn't quite perfect in this decade. And in fact, we could actually have a different name for this section, something like, so, why do we keep having these waste fill failures? And if you look at just the current decade, from 2010 on, there have been a large number of significant waste fill failures in the United States. Some of them are listed here. It's not all of them. I know it's not all of them because some of them I only know about and we only know about because our firm was retained to do a forensic investigation and we promised to keep it confidential. And so I would assume that there are other engineering firms out there that have been asked by other owners to do forensic investigations, and they're not on this list. And hopefully one day all of this information can be shared completely unfettered to the benefit of the profession. But there have been more than one major waste failure per year in the United States in this decade. And I'd like to look at 3 more failures in addition to the ones we looked from historical times, so to speak, and see what the reasons are we're seeing these kinds of events today. And these are, the 3 are highlighted on this slide. They're all 3 that our team at Geosyntec conducted forensic investigations for. And they show some interesting things. So this first project is a confidential MSW landfill in the eastern United States that failed in 2011. This involved a waste and intermediate cover soil interface failure. Not a liner system interface failure like a geomembrane on clay, but waste on a cover soil layer. This is a large landfill. It's about 190 feet tall with 3 horizontal to one side slopes interrupted by benches. And you see the failure mass there. At the time of the failure, waste filling had recently been completed in a landfill expansion built on the 180-foot high slopes of an older part of the landfill. So if you think about, you've got an existing landfill and the owner wants to get more capacity on the site, they're going to put a veneer of fill up the side slope of the original landfill. And that's what they did, 180 feet wide. It was about 180 feet high, 100 foot wide in the horizontal dimension with a liner on the bottom, but no liner up the side slope. The waste was placed right against the intermediate cover soil layer of the landfill. And we'll see that's not such a good thing. In addition, this was a very wet facility. There's a process called leachate recirculation. So a landfill generates leachate, it rains onto a landfill, the water percolates through, you get a contaminated liquid at the bottom, and you use your liner system to collect that material and treat it and handle it appropriately. Well, sometimes facilities will do what's called leachate recirculation, where the liquid that comes out of the bottom, they turn around and pour it back into the top of the landfill. And this was a heavy leachate recirculation landfill. One person I know talked about this and said, this landfill didn't drink responsibly. And so there was a lot of liquid going in. In addition, the stormwater management practices weren't so good, so there was a lot of stormwater infiltration. And then lastly, the landfill accepted sludge, which is very wet and low permeability. So this was kind of the trifecta of conditions to make a landfill wet and not so strong: leachate recirculation, rainwater infiltration, and the sludge. The failure occurred in this expansion area, in this veneer, in a matter of minutes. So very, very fast. 160,000 cubic yards of waste flowed 500 feet beyond the boundary of the landfill. It completely liquefied and flowed out. And you can see on the photograph, if you look towards the bottom, how far the material moved. And you can see that it migrated about 100 feet behind the crest. So the post-failure investigation showed that the slip surface was at the interface between the expansion area waste and underlying intermediate cover soil. And if we look, well, let me just keep going here for a sec. So we conducted post-failure investigations using CPTU testing and other things around the perimeter of the failed area, and determined that there were high piezometric levels in the slope at the time of failure, which was no surprise. On-site observations the day after the failure revealed leachate pools within the waste mass in the failure area, so clearly very wet, and evidence of liquid overland flow 500 feet beyond the landfill. And that was determined, you know, if you've ever seen water rush over grass and the grass gets matted down, outside of the waste that had gone 500 feet, we saw this matted grass, and it illustrated how much liquid there had been in the landfill and how far it had moved. To make matters even more challenging, observers also heard gas escaping from the failure area. And this was perhaps not so surprising because the operating conditions weren't so good in this area, and the active gas management system had only been partially operable for a matter of months. So think of a facility with lots of liquid in it, elevated gas pressures, and sitting there on a slope with a lower boundary, this intermediate cover soil layer, which we see here. So here's a cross-section through the failure area. The darker brown material is the original landfill waste. The lighter brown material is the expansion material that was placed quickly over a matter of 18 months. And you can see the location of the slip surface in the dash red line. And you can see it goes from behind the crest and rides right down on the intermediate cover soil, and then exits at the lowest bench above the bottom of the landfill. And so I've mentioned this intermediate cover soil, and in essence what it did was have the effect of preventing liquid that migrated into this expansion from percolating through it down into the original landfill to the leachate collection and removal system at the bottom of the original landfill. So it acted as a liner. And as a consequence, the material got very, very wet, and failed and flowed, as we see in the post-failure morphology shown in the lower cross-section of this slide. So our team conducted slope stability analyses using the CPTU-derived piezometric levels and the observed location of the failure surface. And through that, they calculated they did a back analysis to calculate an average waste shear strength of 26 degrees based on an assumed 100 PSF cohesion. At the same time, they collected samples of the material, which was estimated to be about 75% municipal solid waste and 25% sludge, and sent them to Ed Kavazanjian at Arizona State University, who conducted strength testing of the material in his 18-inch diameter direct shear box. And Ed's results showed that the material had a secant friction angle of 24 degrees at 10 psi and 20 degrees at 20 psi normal stress, the range of normal stresses of interest in this particular case. And I think, as some of you probably know, these measured and calculated shear strengths are significantly below that which we would normally expect for typical municipal solid waste, whatever typical means in this event. So what can we learn from this case study? First, that excessive leachate recirculation and stormwater infiltration can lead to the buildup of elevated liquid levels and pore pressures in the waste. So once again, we see a problem with liquids. Secondly, vertical expansions that involve the placement of new waste over old need to account for the interface conditions. In this case, a low permeability intermediate cover layer impeded leachate percolation from the expansion area down to the original liner system. Either the cover needed to be removed, it needed to be seriously breached, or a new liner system needed to be put on top of it for the expansion to get the liquids out of the expansion area. None of those things were done. Thirdly, gas collection efficiency can be greatly reduced in excessively wet landfills, both through operational problems, such as the flooding of gas wells, and by the reduction of MSW gas permeability at high levels of waste saturation. And we clearly had high levels of waste saturation in this particular case. And then finally, the effect of sludge on the strength, permeability, and degree of saturation of the waste mass must be accounted for. Okay, this fifth case study is a little bit different. This is in the southern U.S., and it involves a waste mass and foundation failure. In the photograph, we're looking at the slide. That's a landfill slope with a crevasse at the backside, and this waste mass has moved laterally about 25 feet from east to west in the photo. This is an interesting story. The landfill cell was constructed in a 60-foot deep excavation into an over-consolidated native fat clay. Highly over-consolidated, highly plastic material. Now, the excavation occurred in 1996 to obtain borrow soil for operations at the site, but the cell construction did not begin until 2007. So think about it. For a decade, this excavation in this over-consolidated, highly plastic material remained open to rainfall, to ponding, and it was only after that that the landfill cell was constructed. So put your soil mechanics hats on for a moment and think about what could have happened. I should mention the excavation was not only for the cell we see here, but also for a future cell to the right-hand side. So the excavation extended beyond this cell and didn't confine the face. So there was no major buttress. There was a small buttress in terms of a small perimeter berm, but there was no major buttress due to the back wall of an excavation that would have buttressed this cell. So waste filling occurred over 4 years from 2007 to 2011. So remember, open excavation, open for a decade, then start filling, build a liner, start filling the cell, and fill it over 4 years. And it created a slope 95 feet high, inclined at 4 horizontal to 1 vertical. Well, that's not a very big slope for a major MSW landfill. And one wouldn't expect, it's like, that shouldn't do anything. That should be stable. I should also mention that the cell was underlain by a liner system, but we evaluated the liner system, conducted interface testing and all that, and determined it was not part of the causative mechanism for the failure. So when the waste mass failed, it was through a translational movement that occurred over a several-day period. The mass moved 25 feet over several days, so it was like a slow creeper. And it happened 8 months after filling was complete and after 3.5 inches of rainfall fell in the preceding 48 hours. This is an aerial view of the site. It shows the sliding cell in the middle and the direction of translational movement, an older cell in the back, the location of the inner cell berm, and then the future cell. So the first signs of problems occurred 3 months prior to the failure when north-south oriented cracks developed at the eventual location of the slide headscarp. The owner-operator filled the cracks, but they reopened with time, typically after rain events. So over several months, these cracks are reopening, they're being filled to reopen, mostly correlated with rain. Something's creeping. The slide involved translational movement of 700,000 cubic yards of waste and cover soil, as I said, over several days, over a distance of about 25 feet. And for scale, if you look at the backscarp area of this slide, it's about 1,000 feet long, so 3 football fields. So this is a large mass of material that moved. Post-failure investigation involved cone penetration testing again, drilling, a few piezometers and inclinometers, and laboratory testing. While some investigation was done immediately after the failure, it was only possible to install piezometers at the site about 6 months after the failure. And only one piezometer was installed through the cell, through the liner system into the foundation immediately beneath the liner, and it produced a very low pore pressure coefficient of 0.05. So we don't think that data point is representative of conditions at the time of the failure. We also conducted consolidation analyses post-settlement or post-failure, and they suggested that at the time of the failure, the fat clay in the zone that moved was probably about 60 to 80% consolidated. So while it was partially consolidated, it still had considerable excess pore pressures in it. And based on all of that, it was concluded that the failure involved shallow translational movement in the native clay beneath the bottom of the liner system. Perhaps not a surprise. So laboratory testing was conducted. This plot shows the results of torsional ring shear testing to establish the residual shear strength of the material, which resulted in a residual friction angle of just under 7 degrees. And again, this is for material, CH material, with a liquid limit of about 100 and a plasticity index of about 75. So a highly plastic material. The fully softened shear strength was a little over 13 degrees. With that information, our team conducted 2 sets of analyses to try to better understand the failure mechanism. The first involved using the post-failure geometry, so the geometry of the slide mass after the waste had moved 25 feet, with residual strength values for the fat clay and a factor of safety of 1. And that produced a pore pressure coefficient in the fat clay material of about 0.14, equal to about 15 or 16 feet of waterhead at the location of the sliding surface. With that pore pressure coefficient, then a second analysis was done, and using the pre-failure geometry of the slide, before it had moved 25 feet, the pore pressure coefficient and factor of safety 1, to try to get an estimate of what the operative shear strength may have been at the time of the failure. And when that was done, it was found that the calculated operative shear strength was 10.6 degrees, which you can see is midway between the measured residual shear strength of the material and fully softened shear strength of the material. So our conclusion as to what was happening at this site is that decade-long unloading, i.e. the open excavation, and the negative pore pressures induced in the fat clay as it tried to swell, coupled with the ingress of ponded water through desiccation cracks and slicken sides, led to swelling and softening of the clay material and a reduction of its shear strength to, or at least towards, the fully softened shear strength. So this was the effect of the unloading and the access to moisture over a period of a decade. Unloading and then loading. So as they started to fill the cell, the waste loading, coupled with the pore pressures that we believe existed in the slide zone, were sufficient to induce creep shear deformations along that surface. Remember the cracking over 3 months and filling them in and cracking and filling them in? So the waste mass was clearly creeping and the shear strengths were decreasing until the point that they became low enough that the waste mass slid 25 feet over several days. So from the second case study, just a couple of things that we learned that are worth noting. First, a thorough understanding and application of fundamental soil behavior, pore pressure, response, and slope stability principles should be applied in the siting and design of waste fills. It seems obvious, it gets missed a lot. Secondly, engineers need to not only focus on the design of the waste fill itself, but also the placement of the waste fill in the site-specific geological and geotechnical setting. You know, I've seen people get all wrapped up about, you know, getting the interfaces just right and this and that and making sure that the leachate collection and removal system's just perfect. But you have to remember you're placing that into a geological and geotechnical setting and a hydrogeological setting. And so careful attention needs to be paid to that. And in this particular case, the engineer needed to understand the potential for changes to the foundation soil shear strength due to the unloading and softening associated with the decade-long excavation. So the last case study, this last one of my lecture, this is the Green Tree Landfill in Pennsylvania, and this was a waste mass failure, so it didn't involve any liner system, in 2017. And it involved about 15.5 acres of waste that slid a large distance off of the lined area, as we saw in one of the previous case studies. And sadly, it resulted in a worker fatality. And to give you a sense of the scale of this slide, if you look in the middle of the slide area, you see a truck cab, a tractor-trailer truck with a green cab. And you can get a sense that this is indeed a large failure. So there were signs that something was wrong at this facility. In the weeks leading up to the failure, surface cracking, slope bulging, leachate seeps, and gas venting were all observed. So that there was cause for concern. And the owner recognized this, and they were trying to implement measures to rectify the situation, for example, installing gas wells within the area to relieve gas pressures. The slope failure occurred over about 10 minutes. So once again, we see a very, very rapid failure, starting with bursting of the slope face that had been bulging and then retrogressing back across this 15-acre area. This resulted in the movement of about 220,000 cubic yards of material off of the landfill, covering an area of 5 acres beyond the landfill limit. So again, really a flow slide, as we saw earlier. The area where the failure occurred involved an expansion of a new waste cell against the intermediate slope cover of an older portion of the landfill. So again, this is a veneer configuration like we saw for the southern landfill. It was wider than 100 feet. It was bulkier. Its aspect ratio was wider, but again, it was a veneer configuration. And once again, the intermediate cover soil layer was a bad player in all this. The intermediate cover on the old landfill was made from cuttings, waste that were cuttings from oil and gas operations that was blended with lime to stabilize it. This was in Marcellus shale country, and so they were taking these drill cuttings, blending them with lime, and they used it as an intermediate cover soil layer. This created a hard, smooth, and impermeable intermediate cover layer. Not a good thing. And again, there was no removal of the intermediate cover layer, no breaching of it, and no overlying liner system or leachate collection and removal system was installed. And at this site, just like at the earlier site, in addition to municipal solid waste, the landfill accepted a variety of special waste, sludges, which they described as low shear strength wastes, or LSSW. And gas was also an issue here. Prior to the failure, problems were encountered in installing these gas wells I mentioned. In fact, it was kind of a tip-off as to what was going on. As the gas wells were being installed and they encountered LSSW at depth, the LSSW shot up the well bores, indicating that the LSSW was pressurized and not a good condition, so that you know you have a low shear strength waste under pressure, and you also can't get your gas wells in. So the landfill was thoughtful in a lot of ways. The operations plan for the landfill required that this LSSW only be placed 100 feet back from the slope of the landfill. The thinking was, if we have 100 feet of well-compacted municipal solid waste, it'll buttress the low shear strength waste in the middle of the cell. So a good idea, right? Well, the setback had some unintended consequences. It limited the cell area in which the LSSW could be placed. The geometry of the cell was such that once you made this 100-foot buffer all around, there was a relatively small area to place the LSSW. In addition, the facility was only getting enough municipal solid waste that once it built the buffers, it didn't have enough MSW left to mix with the LSSW, so you had concentrated LSSW. And you see that in this figure, the dark brown areas that were determined through CPTs and borings shows areas of highly concentrated LSSW within this failed landfill area. So as a result of all this, the interior zones in the cell, which are shown in brown, had high proportions of LSSW, which is an unintended consequence of the operating procedure, and ultimately created weak zones, which contributed to the failure of the cell. And it's interesting, while the landfill only accepted 20% LSSW, there were zones within the cell that were found to have well in excess of 40% LSSW content. In fact, up to 60 or 70% in some cases. So our team collected representative samples of the MSW and the LSSW, and they sent them to Chris Bareither and Joe Scalia at Colorado State University, who, under the direction of Craig Benson, and I should mention Craig was a collaborator with us on this project. We worked for the owner side by side. They conducted direct shear tests on the waste material in LSSW using Craig's direct shear apparatus design, which is almost 280 millimeter diameter device. We see the results of the shear testing in this slide, and I'll point out, if you look carefully, there's a dashed black line with an intercept at about 24, 25 kilopascals, and then a slope angle of about 33 degrees. That's a representative strength criterion for typical municipal solid waste. And what we see is that for mixtures of MSW and LSSW up to about 40%, the measured strength values more or less fit around the typical MSW strength line. Now, I was surprised by that. I would have expected by 20% LSSW, we would have been seeing reductions in the shear strength of material. And I mention that not because there's anything wrong with these results. I think this is a unique case. I don't want anyone to leave here today thinking you can put 40% LSSW type material into a solid waste mix and have something that is as strong as typical solid waste. And then by 70 to 80% LSSW, which were contents that were seen in the landfill cell, the mixture behaved similarly to a saturated sodium montmorillonite. It had almost no strength. So this combination of factors, this low shear strength material, the smooth, hard, intermediate cover soil that had low permeability and didn't let leachate percolate in, the high liquid and gas pressures, and the LSSW all contributed to the failure and to this flow type phenomenon that we've now seen several times. And it's worth mentioning that, you know, as a result of, you know, you think about societal factors, as a result of the recession in the late 2000s, the amount of municipal solid waste going into landfills dropped quite a bit. this was also aided by recycling efforts and all those kinds of things. And one of the consequences is that the landfill companies, had their salespeople go out and try to find new sources of waste revenue because they have a lot of fixed costs. And so you start taking more of these special wastes that have different properties. If you don't think through carefully what the consequences of that are going to be, you can have these kinds of events. And I think that's one of the macro things that's been going on in this decade. So the lessons learned for this, very simple. Special waste can create operational problems. And if you try to develop procedures to mitigate the problems, if you're not careful, they can have unintended consequences. LSSW, if placed at too high a mass fraction and if not thoroughly mixed with MSW or other stronger material, will create weak zones that affect waste stability. And low permeability zones in the waste, whether it be from LSSW, intermediate cover layer, or anything else, trap liquids and gases in the waste fill, causing fluid pressures to become elevated and decreasing the stability of the fill. So, I presented 3 historical case studies, 3 more recent case studies, and I'd like to conclude with just a few observations and recommendations in light of what we've learned. First, I'd like to show this plot. This is from a paper prepared by Silva, Lamb, and Marr in 2008, appeared in the IFCEE Geotech Journal, Probability and Risk of Slope Failure. And Alan's here today. We talked a little bit about this last night. And it shows the annual probability of failure for a geotechnical structure on the vertical axis versus factor of safety on the horizontal axis. And there's 4 curves there shown on the plot, 1, 2, 3, 4, representing various levels of design, construction, and operational rigor. So the best facilities, category 1, are designed to the highest standard, constructed to the highest standards with quality control, quality assurance, and then operated in accordance with the requirements. And category 4 are structures that have very little engineering associated with them, maybe no engineering, and they don't get nearly the engineering attention and construction attention that category 1, and then there's category 2 and 3 in the middle. And the authors very nicely in their paper describe how they came up with these curves. And they also presented their interpretation, their estimation, and they discussed how they did that of the average, of the probability of, annual probability of failure for what they call the average earth dam, kind of designed to the standard of care in the profession, and came up with an annual probability of failure of 1 times 10 to the minus 4, or 1 in 10,000. And then for the best designed dams, the most conservatively designed dams, earth dams, a probability, annual probability, 1 times 10 to the minus 6, or 1 in a million. And that's based on a factor of safety of 1.5. So most landfills are designed with a static factor of safety of 1.5 because of regulations. That's often the convention. And we've had here in the current decade a number of failures, and we know how many landfills are out there, so we can do a simple calculation and make an estimate of what, in this decade, the probability of failure is for landfills in the United States designed to a factor of safety of 1.5. And when you do that, you calculate a value of 1 times 10 to the minus 3, or 1 in 10,000. That's a probability of failure for landfills that is 10 times higher than for the average earth dam design. It also reflects inherently a design rigor, design quality, somewhere between category 2 and category 3, based on Alan's set of curves. To me, that's a very interesting result. I put some bands on that because obviously not every landfill is designed the same. There are probably some landfills that have higher probabilities of failure. That would be down on the plot due to less rigorous design, but probably not too much lower because of regulations and the standard of care and the threat of litigation if you don't do things reasonably the right way. And some landfills clearly have probabilities of failure that are significantly lower than that average because of the commitment of the owner to do things right, the quality of the engineering, the quality of the data, et cetera. But I think it does show us that there's room for improvement. I've also put on this plot, way up there, a point for U.S. Department of Energy low-level radioactive waste disposal facilities, type of facility I've had the good fortune to work on a number of these facilities over the past 20 years. And the processes that go into the design of these structures are essentially what you would call nuclear quality assurance level 1. So they're designed to very rigorous standards. All the input data needs to be validated. All the computer programs need to be validated. Every calculation needs to be verified. You know, there's checking, cross-checking, back-checking. There's quality assurance at every level. It follows into the testing of materials in construction and in operation, et cetera. And there aren't a lot of these materials. So in Alan's paper, you know, they talk a lot about expert judgment. And so I used my unilateral expert judgment to put this point at 10 to the minus 6. But I think it's reasonable. I'm not being flip about that. I think and the point is, it shows that the technology is there to do things really right if that's the need and that's the commitment of everybody involved. So the takeaway from this slide is that the solid waste industry, and I would venture to say perhaps the mining industry and perhaps, you know, coal combustion residuals, as we're learning about those materials more and more. There's room for improvement in all those areas, and I would encourage that, and that is one of my takeaway recommendations to the profession from this lecture. Then just a few final observations and recommendations. The first is relearning the lessons from 20 to 30 years ago, and I think that's always, you know, like, any part of our profession, I think you could have that, relearning the lessons from 20 to 30 years ago. And, you know, we saw that in some of these failures. That we're seeing the same thing that we saw in 1988 at Kettleman or 1989 at Crossroads, et cetera. And that involves, you know, the need for thorough geotechnical site investigations and in-depth understanding of soil behavior and foundation response. It's critical. You can't design these things if you don't understand your site conditions and you don't understand basic geotechnical engineering. Operating conditions in the field can and often do deviate from the design. We saw that in a number of the case studies today. This requires coordination between the owner-operator and the design engineer. Field deviations from design should be pre-checked by the design engineer before they're implemented in the field. And a cautionary note, design engineers and owner-operators need to avoid complacency in a maturing industry and recognize that waste fills are large geotechnical structures with large failure consequences. Still relearning here. It's essential that waste properties be reliably evaluated or conservatively estimated for design. Now, the good news here is that a ton of work has been done, a lot of very good work has been done with respect to municipal solid waste. And there are a number of people in the audience that have led those efforts. I think today the challenge lies to some degree with special waste and special waste MSW mixtures and recirculation landfill waste and elevated temperature landfill waste. And in other areas, things like coal combustion residuals and certain types of mine tailing wastes. And so we know we need to be thinking about the properties of all these types of materials. And I would encourage and recommend project-specific waste testing for any of these conditions. It's essential that design engineers have a thorough understanding of the shear strength and deformation behavior of all interfaces that will exist in the structure. We learned that 30 years ago at Kettleman Hills. We're still learning it today. And I'll repeat what I said earlier. Project-specific soil and geosynthetic interface testing should be conducted if there's any doubt about the adequacy of available databases to represent the project-specific conditions. Some more recent lessons learned, I only have a couple slides and I'm done. Aggressive leachate recirculation to accelerate waste biodegradation and to reduce leachate disposal costs for owner-operators has had a number of unintended consequences that can impact stability. This is includes the buildup of liquid heads in the landfill, watering out of gas wells and saturation of the waste, reduction in gas permeability at high degrees of saturation, and increasing landfill temperatures, which can lead to faster, greater waste degradation. So the recommendation is that recirculation rates need to be moderated and landfill internal drainage features need to be enhanced when recirculation is used. In addition, I would recommend better water balance evaluations for these facilities, looking at liquid inputs and outputs to understand whether you're building up liquid levels within the facility. This will have a cost to the owner-operators, but also a large benefit in terms of fewer stability issues, fewer elevated temperature issues, and such. And then, where the rubber meets the road, the owner-operators need to manage their facilities to comply with the specified operating conditions. And you can't have renegade site operators that, when no one's looking, do what they want to do. Co-disposal of special wastes with MSW can lead to geotechnical stability and other problems. We saw that in a number of the landfill failures today. So the recommendation is that owner-operators should have their engineers develop detailed special waste acceptance plans for each special waste stream. The swaps should consider the influence of the special waste on leachate and gas generation, waste properties, slope stability, operations, and nuisances. Owner-operators must ensure that their field personnel then follow the swaps. And unintended consequences, as we saw in several of the case studies, need to be carefully considered and addressed. So we can't go off, without really carefully considering, if I'm going to do this in my operations, are there any unintended consequences? And then a high level of operating vigilance is needed in fills that accept special waste. Engineers should integrate the classical observational approach into their operating plans that they prepare as part of their designs. So the last recommendation, set of recommendations, the costs and permitting challenges in developing greenfield sites is leading to the increasing use of vertical and lateral expansions at existing waste sites. We saw that at the Eastern U.S. landfill. We saw that at the Green Tree landfill. Vertical expansion configurations and materials have contributed to landfill failures. We saw that. The immediate cover interface must be carefully engineered for stability and permeability. In some cases, the cover should be removed or at least breached. In others, a new leachate collection and removal system should be installed on top of the cover. And then the effects of the vertical expansion on the properties of the original waste, on the waste at the bottom of the very original landfill, must be carefully considered because it affects density, it increases it, saturation, and it reduces gas permeability. And this can make your original landfill not perform as well as it formerly did. So my last slide, I'd like to close with something from my mentor, Jim Mitchell's 2004 H. Bolton Seed Lecture. The title of the lecture was Geotechnical Surprises, or Are They? And in the paper, the lecture and the paper, Professor Mitchell looked at a number of failures and asked the question, are these surprises or are these things we could have understood or anticipated if we had approached the problem in the right way? And he concluded that these failures, the things that led to these failures could have been anticipated. And he said some of the main reasons that we often fail to identify the appropriate factors and potential consequences that lead to geotechnical surprises are. And he had a list. It's a great list. And it's shown here. Now, I've made it a bit more artistic than his list, but, and I'm not going to go through it, but I'll just say many of the things he described are some of the things that led to the problems in the 6 case studies we looked at today. And with that, I'll conclude and say thank you very much.